Good morning, everybody. Today we are discussing the next topic of the stereochemistry, that is condition for optical activity. So, a substance that can rotate the plane polarized light is called as optically active compound. So, the necessary condition for the optical activity is the property of the chirality. So, what do you mean by the chirality? Chirality means every organic compound contain the carbon as the central metal atom, and this carbon have 4 valency. If it is satisfied by the 4 different substituents, we call it as a chiral molecule, or it does not have any element of symmetry. Or if a carbon atom have the different spatial arrangement of atom and it have the capacity to rotate the plane polarized light, then it is an optically active molecule. Majority of the optically active molecule will contain the chiral carbon atom. So chirality is the property present in an object that cannot be superimposed on its mirror image. And chiral object or a chiral molecule do not have a plane of symmetry. We have already discussed some of the element of symmetry, and we have studied the element identity, axis of symmetry, plane of symmetry, and inversion center and center of symmetry. So in which if it is a molecule, if our molecule is a chiral molecule, it do not have a plane of symmetry. And that molecule is an asymmetric molecule since it do not have any element of symmetry. That's why this molecule must be an asymmetric molecule. So we have studied in 4th semester the difference between asymmetric and disymmetric molecule. Asymmetric molecule means the molecule which do not have any element of symmetry. And disymmetric molecule means a molecule which do not have a plane of symmetry. So every asymmetric molecule are disymmetric, but every disymmetric molecule are not asymmetric. Now we are moving into how we will measure the optical activity of an organic compound. The optical activity of an organic compound can be determined by a term, that is specific rotation. So specific rotation is represented by alpha. So alpha is equal to alpha observed, that is observed rotation of a optical rotation of our compound, divided by C. C means it is the concentration of a organic compound in the unit of gram per ml. And L is the path length in decimeter, and alpha observed is the rotation observed for a specific sample. So usually this is the equation which is used for measuring the optical activity of an organic compound, and the alpha is known as the specific rotation. How we will measure the optical activity? By using a polarimeter, we will dissolve the organic compound in appropriate solvent, and we will fill the sample in a cuvette or a tube, and which is filled in a polarimeter, and we measure the specific rotation. If it is a original compound, we will get the optical rotation as the standard compound, optical rotation of a standard compound. So whether the optical activity of our sample and standard sample is matching, then we will ensure that our compound is pure. Next is the optical purity and how we will measure the optical purity. Optical purity means if we have a racemic mixture means it is a mixture of 50% of the D variety. That means 50% of the organic molecule which rotate the plane polarized light towards the right, and the remaining 50% is the L variety. That means the organic compound which rotate the plane polarized light towards the left. So if the mixture containing 50% D and 50% L variety, then we call it as that molecule as a racemic mixture. So optical purity means if any one of the enantiomer in a mixture is excess, then that excess quantity we call it as optical purity. So for a racemic mixture, the 50% L and 50% D is present. So there is no excess of any enantiomer. That's why the optical purity of racemic mixture is equal to 0. So the definition of the optical purity is as a ratio of the observed optical rotation of our sample, which consisting of the mixture of enantiomer to the optical rotation of one of the pure enantiomer. So optical purity is expressed in terms of an equation. Optical purity is equal to alpha of the mixture, that means specific rotation of that mixture, divided by alpha of the enantiomer when it is a pure compound, and into 100. Usually optical purity expressed in terms of percentage. Now we have another term, that is enantiomeric excess. So both the optical purity and enantiomeric excess both are same, but only the difference is that optical purity means excess quantity of the enantiomer. Enantiomeric excess means the difference between the percentage of the two enantiomer in a mixture. So we can express the definition in terms of mathematical representation. Enantiomeric excess is represented by small e, that's equal to percentage of the R, that is dextrorotatory compound, minus percentage of the S, that is R variety. The R and S are the configuration of the molecule, and that is percentage of R minus percentage of the S. So this is the enantiomeric excess. Now we are moving into one of the example. See here, the first figure is the plane polarized light, and if the plane polarized passing through a amino acid. So the general formula of the amino acid is RHNH2COH. So if it is passing through a amino acid, always remember that every amino acids are optically active. So the plane polarized light is rotated towards the right direction. So the measured optical rotation is alpha observed is equal to plus 14. That means this organic molecule rotate the plane polarized light towards the left, and the magnitude is 40. So if it is matches with the standard compound, then we can call it as our molecule is pure. So that is represented by the blue bar, which shows that 100% of the plus enantiomer is present in the in our analyte solution. So the next is the again plane polarized light passing through an amino acid. See, the difference between these two amino acids is only the position of the NH2 and hydrogen. In the top of the slide, we can see NH2 is in the backward direction and hydrogen is in the side of a viewer. But in the bottom of the slide, we can see that the position of the hydrogen and NH2 is changed. So when the plane polarized light passed through this amino acid, we can see that the alignment or the plane polarized light is rotated towards the left, and the magnitude is same, only 14, but the value is a negative quantity. Alpha observed is minus 14. And since it is an opposite direction, that's why it is also a 100% pure compound, and the value magnitude is matches to the standard value. That means it is our analyte solution is the pure compound, but it is a enantiomer of the other variety. Okay, that is shown in the bar, red colored bar. So which is the next variety of the next enantiomer of the same amino acid. Now we are moving into enantiomeric excess. In the first example, we can see that it is a mixture of the enantiomer, but it contains 90% plus variety. Plus means it is a dextrorotatory compound, dextroenantiomer, and the remaining other 10% is the levo variety. So if it is mixed together, how we can measure the enantiomeric excess? So enantiomeric excess is the percentage of the R minus percentage of the S. So here it is 90 minus 10. So we'll get 80 as the answer. So what is happened in the in that mixture? See here in the first box I have shown by the 10% anti-clock and shown by the green color. So in the racemic mix, in this mixture can be split into 10% of the anti-clock and 90% of the clockwise compound, enantiomeric compound. When we mix together, the 10% of the anti-clock molecule is compensated by the 10% of the clockwise molecule, but there are 80% remaining in the mixture. That is our enantiomeric excess. So the next example, a mixture which contains 60% plus enantiomer and 40% minus enantiomer. So what is the enantiomeric excess? Enantiomeric excess is 20. We will get by enantiomeric excess EE is equal to the 60% R minus 40% S. So 60 minus 40 we will get 20. This is the representation of this calculation. The 40% anti-clockwise and 60% clockwise, if we mix together, the 40% of the anti-clockwise compound, enantiomeric compound, is compensated by the remaining 40% of the clockwise, which is shown by the red color bar in the cuvette, and we can see the excess enantiomer which is shown by the blue color. So that is only a 20%. So the last example, 50% and 50% of the enantiomeric compound, that means it is a racemic mixture. We can see that we can calculate the enantiomeric excess is equal to 50% of the R minus 50% of the R, that's equal to 0. So racemic mixture always have an enantiomeric excess as 0. So this is the representation of this equation. See here the 50% of the clockwise direction and 50% of the anti-clockwise direction compensated together. So there is no excess enantiomer which is shown in the blue color. So that's why the enantiomeric excess is 0%. Now another example, in this mixture we have 70% X and 30% R. So how we will measure the enantiomeric excess? Simple, enantiomeric excess EE is equal to 70 minus 30, that's equal to 40%. So I hope that you understood the concept. Thank you.